Section 4.5, properties of logarithms. So let me give you some properties of logarithms. So let's assume m here is greater than 0, n is greater than 0, b is greater than 0 and not equal to 1, a is greater than 0 and not equal to 1. So property number 1. The log of a product is the sum of the logs. So log base b of m times n is just a log base b of m plus a log base b of n. So if you wanted to multiply two numbers, you could just take their log and add them. So back when Napier was inventing logarithms, the reason he invented logarithms is because they didn't have handheld calculators back then. So to take a product, it's much easier to add than multiply. To take a root, say if you have a number with 10 decimal places and you want to take its fifth root, do that by hand. It's not so easy. And then, and that's one calculation, in a list of 50, you have to do, multiplications, divisions, a whole bunch of roots and all that. It's going to take you a long time. If you can make it where it's just adding and subtracting, then it's much easier. So to take a product, you just take the log of a product, and it gives you the log of products, same as the sum of their logarithms. To take the log of a quotient, log base b of m over n, you just subtract the logarithms. So log base b of m minus log base b of n. To take a exponent of you just take the log of an exponent, and that's just the exponent times the log of the base. And so the log base b of m to the r is just r times the log base b of m. So that makes taking roots and all that very easy. You're just multiplying. So that's a much easier operation. Always 0 for any base b where it makes sense. The log base b of b is 1. The exponential function and the logarithmic functions are inverse functions of each other. And so the log base b of b to the x is just x. And similarly, b to log base b of m is just m. The change of base formula. Log base b of m is equal to log base a of m divided by log base a of b. So this means that you can switch between bases just base formula. So it really doesn't matter what base you use. So initially, we would always use the common logarithm because we didn't have calculators. But past the year like 1970, when everyone started to buy and manufacture handheld calculators, all formulas past that date are done in natural logarithms. And that's because the mathematics is easier if you use, and the formulas will be easier if you use natural logarithms. So what you'll notice is that some of the formulas that we come up with are done with common logarithms, and that's because they were before 1970. But after 1970, they're all all done in natural logarithms. Rewriting the change of base formula, I can write it as follows. Log base A B times log base B M, notice the B's are the same, is just log base A of M, quote unquote. The B's just sort of get absorbed. The log, if, since the logarithm is an inverse function of an exponential function, and exponential functions are injective, so are logarithmic functions. The log base B of M is equal to log base B of N implies that M is equal to N. Similarly, since the exponential function is injective, the log base, the exponential function B to the M equaling B to the N implies that M is equal to N. Some formulas. Acidity. The pH is equal to the negative of the log of the hydronium concentration. So it's this bracket H plus is just the concentration of the hydrogen ions in your solution. Weber-Fechner. L is equal to K ln I, where L is the apparent loudness and I is the intensity. Do some examples. Page 468. Problem number 37. Assume that X, Y, Z, and B are positive numbers and B is not equal to 1. Use the properties of logarithm to write each expression in terms of logarithms in X, Y, Z. So this is equal to, recall, the log of a product is the sum of their logs. And if you have an exponent, you can bring exponents out in front of logarithms. So let's rewrite this. I will bring the 7 outside. Since we're multiplying, I'll just put a plus. I'll bring the 8 in front of logarithm. Write the ln y. So notice that the exponent of y was 8, so I put that on front. Since I'm multiplying the x to the 7 and y to the 8, I add, and I bring the 7 out in front, which was an exponent of x. And that is your answer. Let me do next problem. So assume that x, y, z, and b are positive numbers and that b is not equal to 1. Use the properties of logarithms to write each expression as a logarithm of one quantity. And so I just want that this is equal to ln of one quantity. Since I have a negative in front of this quantity, then this will go into the denominator. So my x will go into the denominator. Since I have an exponent of 2 out in front, then this will be an x squared. Next, since I have a negative outside the logarithm, that means that this y will go into the denominator, and they'll have an exponent of 3. Since there's a plus here in front of this log of z. The z will go into the numerator. And I'll have an exponent of 1/3, which is the same as a cube root. And that is your answer. Okay, so the next one, determine whether true or false. Okay, so problem number 54. So, log base b of 1 over a. Is that equal to negative log base b of a? Yes. So this is a true statement. So log base b of 1 over a is the same as log base b of 1 minus log base b of a. Well, the log base b of 1, so this is 0. And so this is equal to minus the log base b of a. So yes, this is a true statement. Okay. Let's do problem number 54. Log base b of x plus y is not equal to log base b of x plus log base b of y. Yeah, that's certainly a true statement. They're not equal, meaning that if you plugged in, let's say, for example, so this is certainly false. So this is a true statement because they're not equal. For example, log base b, let's just do natural. So log of 2 plus 5. If you plug these in, let's actually do 100 plus 10. Let's see if this is a true statement. Log of 110. Is this equal to, log of 100 is 2. Log of 1 of 10 is 3. But the log of 110 is something weird, is, approximately 2.04, whatever. And so these are not equal. So since they're not equal, then that's a true statement because it was saying, are these not equal? Yes, they're not equal. Okay. Use a calculator. We'll do 4 decimal places. They told us how many places. So that's good. Use a calculator and the change of base formula, round to 4 decimal places. You can either use the natural logarithm or, you can use any base you want to change to, but on our calculator, we only have 2 bases, either base 10 or base e. I will use base 10 for no particular reason. If you did base e, you'll get the same answer. But let's do log, the common logarithm. So of 3 is just log 3 over log 7. And so that's your answer. And so let's plug that into a calculator, and I get 0.5645750341 to 4 decimal places 6546. And that's your answer. Okay. Let me do 105. So let me do problem number 105. Weber-Fechner law. What increase in intensity is necessary to quadruple the loudness? So I want to make it 4 times larger. So I have here that L is equal to K ln I. So I want to quadruple the loudness. So if I want to make it 4 times larger, that's right. Let's bring up K, the 4 exponent. So this is ln I to the 4. So to increase this by a factor of 4, you have to raise the intensity by a factor by 4. And so you must raise the intensity to the 4th power. To quadruple the loudness. So that's quite a bit. You have to raise it to the 4th power. Let me do 108. Okay. Moving. There. Okay, 1 second. Let's move this up too. Okay, let's move this up. There. And move that. Okay. And move this. Okay, so now, Richter scale. By what factor must the amplitude of an earthquake change to increase its severity by 1 point on the Richter scale? Assume that the period remains constant. The Richter scale is R equaling log A over P, where A is the amplitude and P is the period of the tremor. Okay, so I start out with a, why is it not moving? Here it is. Good. It started to move again. So I start out with a earthquake having the following amount on the Richter scale, the earthquake of this intensity. Suppose that I increase by 1. So this is just going to be the log of A over P plus 1. Recall that the log of a base, well, the log base B of B is equal to 1. So if you take the log of its base, you just get 1. So the common log is 1. Next, recall that if you have 2 logarithms and you're adding them together, that's the same as the log of their product. And so to increase the Richter's, the amount of the earthquake by 1 on the Richter scale, well, I'm just going to multiply by 10. So this is just 10 A over P. And so you have to increase the amplitude by a factor of 10. So you have to, it has to be 10 times larger amplitude.